proper statistical test. I mean, we've kind of done a few, unbeknownst to you, but now it's official. So let's dive into it. We're going to be looking at one sample t-tests, translating some numbers again, doing some examples, and showing you some examples in R. Let's get on with it. One sample t-test. Griffin, you've already done some of this with the z-test that you calculated and a few actual t-tests we did in our last lesson. But now we are going to focus exclusively on the t-test, and here is our equation again. It shouldn't look too different. We have our x bar, so the sample mean that you went out and calculated, our mu, and our standard error down here. So there are a few different types of t-test. For this lesson, we're going to focus on the one sample t-test. So what's the purpose of a one sample t-test, you might ask? Maybe you're not, but I'm going to tell you. A one sample t-test compares the mean of one sample, the mean that you went out and calculated from your sample, to an assumed population mean like a national average, to determine if the sample is truly different from an assumed population. That's the whole goal. So for example, remember we looked at a group of students that receive statistics tutoring versus the normal population of those that do not? We want to know if there is a statistically significant difference between their means. Let's have a look at the one sample t-test formula again. Let's break it down a bit. Here we have the sample mean you calculated and some sort of population mean that we want to compare against. Now here, when you subtract that mean from your sample, we're going to end up with the difference, right? Then we're going to divide that difference by the standard error. So we are transforming this difference into the standard error language. And what this does is it standardizes it into a t-statistic. And what can we do with t-statistics? We can go and look them up on the table to see their corresponding proportions or probabilities. So let's do an example. The freshman 15. You've heard that the average amount of weight change for the first year of college is plus 15 pounds. To test this claim, you take a sample of 25 UT sophomores and ask them to report the amount their weight has changed during the previous year. You calculate summary statistics for your sample and you get a mean of 13 pounds, so plus 13 pounds, and a standard deviation of 4 pounds. Test the claim of the freshman 15 using alpha of 0.05 and the steps of hypothesis testing. First off, what are the hypotheses, and is this a one or a two-tailed test? Take a moment and see if you can figure that out before we move on. So step one, we state the hypothesis and we draw the picture. Are you drawing the picture? You better be drawing the picture. It helps. So our null hypothesis here is the freshmen gain on average 15 pounds during the first year of college. The alternative is freshmen do not gain an average of 15 pounds during the first year of college. So in this case, we are not making an assertion that it's higher than 15 or less than 15. We're just saying it's going to be different. So we're doing a two-tailed hypothesis test here. Step two, what is the level of significance we want? In the problem it said test at 0.05, and again, that's usually the convention. Step three, what statistical test are we going to use? Well, that's fairly obvious because this entire lesson is called one sample t-test, so we're going to use a one sample t-test. Step four, what are our critical values? We have two of them because it's two-tailed. So we have a two-tailed test, so we'll be looking here, and we're testing at 0.05, so we'll be looking right here. And we have 24 people in our study, but we have to subtract 1, the n minus 1 to get our degrees of freedom, so we will look for 24 over here, and we end up with a critical value of plus or minus 2.064. And here are the critical values on our lovely curve. Ooh, Step 5, calculate the test statistic. Here, just substitute the numbers into the formula. This was your sample mean 13. We subtract the population mean that we're testing against, divided by the standard error, and we get negative 2.5. So where does this fall on our distribution? Will it be significant? The anticipation. And this is what our t-statistic and our t-criticals look like on our curve. Also notice that here I have translated these critical t-values into their corresponding raw scores. So the raw score, or the raw value that corresponds to a critical value of 2.064 in our example is 16.6 pounds, and on the negative side it's 13.35 pounds. Now you can see that our sample mean of 13 is less than that 13.35. It's far enough out into that red region. So what do you think our conclusion is going to be? Step 6, make a conclusion. Because our t-statistic, negative 2.5, is past our critical value, past negative 2.064, in that critical region, we get to reject the null hypothesis. We could also, because I've translated the numbers, see that our sample mean of 13 is far enough away from 13.35, it's in that critical region that we reject the null hypothesis. The true average amount of weight gain for UT students is not 15 pounds. Let's think of this critically. Our results were statistically significant at the 0.05 level, but what does that mean practically? What could it mean in regards to the sampled group? Maybe UT students don't gain as much weight. Maybe Austin is a healthier city. Maybe you sampled some athletes and your weight was not representative. Also, it would not have been significant if it was just 0.35 pounds more. Notice how close that was. So if here is our null world, we are still far enough away from it, but barely, just barely. Translating numbers again! As you've noticed, I have a thing for translating between standardized and the raw. I've included numbers in the standardized t-scale and the numbers in the original scale in some of my questions. This is not convention, but I find it makes the ideas more tangible and helps in understanding. You can same conclusions as your t-test, but the scientific community prefers standardized numbers because we don't always know what your scale is and we're not familiar with it. You still have to report your t-statistic, but if you really want to double check, here's how to do it. So here is how you translate those critical values back into the raw numbers. So instead of creating the confidence interval around the mean that you went out and collected around your sample, we instead are going to kind of make a confidence interval for our null. So everything here is exactly the same as our regular confidence interval equation. The only thing that's now different is that instead of using the point estimate, now we are going to be using the null value, whatever value it is that you're testing against. So here is our freshman 15 example, where I take the 15 pounds, that's the value we're testing against. We use the t-critical value that we looked up, and we multiply it by the standard error. And you end up with 16.65 and that 13.35. And that is how you translate them. Here I am visualizing that confidence interval we put around our null. So we have that 13.35 and the 16.65, and those are the kind of brownish orange colors for the null. But I also then created a confidence interval around our actual point estimate, our sample mean that we calculated, that 13. And it's 11.35 over here, and you can see it here, and 14.65 right here. Now, what do you notice about this alternative, this point estimate confidence interval we made here, and the one over here? Did you notice that our confidence interval we created around our point estimate of 13 does not contain the population parameter we were testing against, that 15? Similarly, our confidence interval around our null does not contain 13. So considering the sample size and the standard error, the sample mean of 13 is not a reasonable value in this null world in our example. It is extreme enough for us to conclude that the probability of seeing a sample mean of 13, if the null were true, is less than 0.05. So we reject the null hypothesis. So what are one-sample t-tests for? One-sample t-tests are for situations when you are comparing your sample mean to a known population mean, so a mu. Some examples of this might be, did this school district score lower than the national average? Or are UT students more or less likely to gain the national average of 15 pounds their freshman year? And also, t-tests are always for situations when sigma is unknown. If sigma was known, we would do a z-test instead. Up next, one-sample t-tests are for one sample to compare against one known population mean. But what if I want to compare two groups that we sampled? For that, we need an independent samples t-test. But first, we're going to take a quick detour to effect sizes and Cohen's d. I'll see you in that one. One-sample t-test in R. So here is the one-sample t-test in R with that freshman 15. First off, you need to tell R, of course, all the information that we have, so our sample mean, population mean, standard deviation, n, and our degrees of freedom. Then we need to get our critical values. So we use that lovely QT function, and we put in the corresponding values that correspond to 95% confidence, or that 0.05. So here we put 0.025 and 0.975, and then we tell it the degrees of freedom. And it will tell us the two critical values associated with that are negative 2.064 and positive 2.064, which is what we saw earlier. Now to actually calculate the t-test, very simple. We take our sample mean minus our population mean divided by our standard error, which is standard deviation divided by the square root of n, and we get negative 2.5, which is what we got in our example. And in this case, we would reject the null hypothesis because this is further out than this. And here is how you get the confidence interval for your point estimate of 13. We get the critical value, which we already got, and we multiply it by the standard error to get our margin of error. Then we just add that margin of error to our sample mean. Now you might notice, well, why aren't you doing the adding and subtracting part? Our margin of error in this case has two values because it was a two-tailed test. This two-tailed critical thing had two numbers inside it. So it got stored as two numbers, the positive and the negative. So you just have to add it and it will give you the confidence interval of 11.35 and 14.65. Now in most of the examples we do, we're using summary statistics. So I tell you what the average is and the standard deviation, but in reality, normally you'd be using a full data set that has all the observations and you'd have to calculate the mean and the standard deviation and all that jazz. Thankfully, R is wonderful and it can do it for you very quickly. And if anything, it's probably easier to do this with a clean data set than it is to do what I just showed you. So here's an example. There is a data set in R that you already have, and it's called insect sprays. And it's the number of bug bites people get with certain different types of insect sprays. So I'm calling that data set, and I'm going to call it data. Now to do the t-test, this is all we have to do. We say t.test, very original. Then we specify the data. So we say x equals data, $, count, because the count is how many bug bites somebody got. Then we have mu, which is 14. I just made it up, maybe the average number of bug bites we get in the summer, getting eaten alive. So 14 bug bites is the average we're going to test against. And we're going to say two-tailed, because maybe this bug spray attracts insects, so maybe it'll be higher. So that is how you would do a two-tailed. Now real quick, this is how you would do a one-tailed, because we would think that if you're spraying bug spray, you should have less than 14. So what kind of test would that be? So one-tailed, but is it left or right? It would be a left tail, because it's a less than. So you just tell R, I want you to do, instead of the alternative being two-sided, I want the alternative to be less. You could also tell it greater if you wanted to do a right-handed one-tailed test. So now let's see what the output looks like. Ta-da! Nice and simple. So here, R will tell you the t statistic, so -5-ish, degrees of freedom, 71, and this incredibly tiny p-value, so that's a lot more specific than p less than 0.05. It will also give you a confidence interval and the average of your sample. So all the work is done for you. Now we can also look at this one down here, and this is our one-sided test. We have a similar t-value, we have the same degrees of freedom, which makes sense, a even lower p-value because we put all that probability on one side, so it's even more significant. And we have our confidence interval. This negative infinity is a little bit confusing, but we don't need to get into that. And we have 9.5 as our mean, which is the same as the other one. So if you were going to do a t-test in R with actual data, it's super easy. Look at that. Can you imagine trying to calculate everything by hand? So this is great, and I highly encourage you to play with some of the data sets that are already in R, like insect sprays, or some of the other ones that I've posted on Canvas, because this is awesome. It really is. Can you imagine what it was like back in the day? So give it a go. Let me know what you think. Have fun.